Hey guys, so this is part two of the Regents Review multiple choice questions. So, number 12 states a seismic station that is 4,000 kilometers from the epicenter of an earthquake records the arrival time of the first P wave at 10 hours, 0 minutes, 0 seconds. At what time did the first S wave arrive at the station? For this question, you need to go on your reference table, page 11, and you need scrap paper. To find out the answer for this, based on when the P wave arrived, when did the S wave arrive, you need to find the time difference between the P and the S wave. So that's why we are using scrap paper. I'm given that the distance is 4,000 kilometers of the epicenter of the earthquake. So here's the epicenter distance in the x-axis. 4 represents 4,000. I'm going to align my scrap paper at 4, this line for 4,000 kilometers here, and I'm going to align it with the S and P line, and it needs to be vertical. I'm going to draw a line, a small mark, where my scrap paper meets the P wave, and I'll draw a mark where my scrap paper meets the S wave. So I'm marking down how far away the P and S wave lines are at this distance. Then I'm going to take my scrap paper and put it on my y next to my y-axis, the travel time, to find the actual time difference between the P and S wave at this distance. So I'm gonna put one of my marks at 0 and see what my other mark is, and notice that my time difference between the P and S wave at 4,000 kilometers is around 5 minutes and 40 seconds, because each of the small increments are 20 seconds. So now that I know that my P and S wave time difference is 5 minutes and 40 seconds, if my P wave arrived at this time, my S wave must have arrived 5 minutes and 40 seconds later, because the S wave is slower, S for slower. So that's why my correct answer is 2. S wave arrived at 10 hours, 5 minutes, and 40 seconds. I'm just adding 5 minutes and 40 seconds to the P wave arrival time. Next, number 13. What is the approximate latitude and longitude of the Bavette hotspot? The answer is number 2, 54 degrees south and 30 degrees east. You're going to go on your reference table, page 5, and it shows the different locations of the Earth and the hotspots. And this is the tectonic plates. And notice that for latitude and longitude, we start with latitudes first, and we see if our location is north or south of the equator. So here's the equator, the green line. Bavette hotspot is on the south of the equator, around 54 degrees south. That's my first number, 54 degrees south. Next, we're going to determine whether my location is east or west of the prime meridian. And that's why we're looking at the prime meridian first. Here's my 0 line for the prime meridian, my longitude. Bavette hotspot is on the east of the prime meridian, around 3 degrees east. That's why the correct answer is 54 degrees south and 3 degrees east. Number 14 states, as the distance from the mid-Atlantic ridge increases, the age of the ocean floor surface bedrock. The answer is number 2, increases only. If you go on your note packet, your Regents Review packet, page 6, this is the mid-ocean ridge, and it forms in a divergent boundary. In a mid-ocean ridge, as the plates move apart, my older rocks are being pushed away away from the middle of the ridge, and in the middle of the ridge, my magma is rising and solidifying to form new crust. So my younger rocks are in the middle, my older rocks are farther away from the middle of the ridge. So my age is increasing as I'm moving away. Number 15. The photograph below shows an elongated hill that was originally deposited by a glacier. This landscape feature is identified as a number 3, drumlin. This is a drumlin. If you go on your Regents Review packet, you'll see that glaciers, one of the depositional features that are created, and glaciers are drumlins, and they look like this. And this shows the direction of ice flow, the hump. So number 16, compared to the masses and densities of terrestrial planets, Jovian planets have, the answer is number 3, greater mass and are less dense. So if you go on your Regents Review packet, page 21, you'll see that the Jovian and terrestrial planets can be found on your reference table, page 15, right here. The Mercury, Venus, Earth, and Mars are terrestrial planets, the first 4 planets closest to the Sun. And then Jupiter, Saturn, Uranus, and Neptune are Jovian planets, the 4 planets farther away from the Sun. So if you go on your reference table, page 15, you'll see that compared to terrestrial planets, Jovian planets have a higher mass, but they have a lower density compared to terrestrial planets. Number 17, the star Vega has an average surface temperature of 10,000 Kelvin. Kelvin is a unit we use for temperature for celestial objects, and has a luminosity 70 times greater than that of the Sun. Which type of star is Vega? The correct answer is 4, main sequence. So Vega, it has a temperature of 10,000 Kelvin. We're looking at our reference table, page 15. 10,000 Kelvin is right here, and then it has a luminosity 70 times greater than the Sun. Notice that the Sun's luminosity is represented as 1. So if Vega's temperature is 70 times greater, then on this chart, Vega's luminosity should be 70 if a sun's temperature is 1. So here's 70, here's 10,000. I see that Vega must be a main sequence star because all these stars right here are in the main sequence stage. Next, 18. The diagram below represents the moon at one position in its orbit on Earth, which diagram represents the phase of the moon as viewed by an observer in New York State when the moon is location at this position. So notice that it's half black, half white, because the sun's rays are lighting up only half of this, and the other side is dark. But it's asking you what our perspective is from the Earth. How are we seeing the moon? And if you go on your Regents Review packet, page 26, you'll see that the sun is coming from the right side. And if the sun is coming from the right side, the new moon will always be next to the sun. The full moon will always be on the opposite side. And then from the new moon to full moon, my moon will get light on the right side a little bit, and then half light on the right side, and then mostly light on the right side. From the full moon to new moon, my moon will get slightly dark on the right side, half dark on the right side, and then mostly dark on the right side. Based on this, my answer should look like that, number 3. 19. The constellation Orion can be observed from New York State in the night sky during winter, but it cannot be observed in the night sky during summer due to 19 is 2, Earth's revolution around the sun. If you go on your Regents Review packet, one of the Earth's motions is revolution going around the sun, and the evidence is that we can see different constellations in the night every couple months or seasons as the Earth is going around the sun. This is different from rotation, which is the daily movement of apparent movement of the sun and stars in the sky. So if it's related to seasons or months, it's revolution. 20. The block diagram below represents a section of a meandering stream. The arrows show the direction of stream flow. The stream bank on the outside of this meander is steeper than the stream bank on the inside of this meander because the water on the outside of this meander is moving. The answer is 4, faster, causing more erosion. This is because if you go on your Regents Review packet 8, page 8, you'll see that in a meander, the erosion is on the outside curve and deposition is on the inside curve. So if you can draw the capital letter D in the crevices, that's where deposition is happening, and everywhere else is erosion. So and deposition is happening where you're getting the water is slower. That's why the water is depositing all the sediments there. Erosion is happening in the on the outer corners, and erosion happens where the water is flowing faster. It's removing sediments. Because of that, the water has a lot of energy. So that's why the correct answer is faster, causing more erosion on the outside. And that's it.